Good afternoon to one all present here. I request each one of you to keep your microphone and video off. And those who have any question can post your name in the comment box during the lecture. The questions will be answered in the end. I, Abhishek Gade, Chairperson of Nauroji Wadia College SP Student Chapter, take a pleasure to welcome you all to this session of SP Technical Lecture Series. The SPA lecture series has organized a virtual seminar on drilling and completion fluids conducted for 3 days, and today is our final lecture on the completion fluids and the future of the drilling fluid industry. We are overwhelmed to have Mr. Rahul Day as the speaker of the day. I now request Mr. Rahul Day to address our keen listeners.
All right. Thank you, Abhishek, for that introduction. And let's begin. I hope you guys can bear with me for another 30-40 minutes and we'll be through with the workshop. But that does not mean that it ends there. So, of course, you are more than welcome to ask your questions during the question and answer session, or feel free to email them to me. All right. So let's look at the agenda. First, we want to understand what are completion fluids, right? We looked at drilling fluids quite a bit. So what is so special about completion fluids, and why does completion demand its own session? I mean, this workshop could have been completed in one day, could have also had drilling fluids and completion fluids together in one lecture. But why does completion fluid have to have a separate lecture, needs separate attention, right? So those are the kind of things that we would probably look at. Of course, it goes without saying that I will be also sharing some kind of insights that are from my personal experience. So feel free to post questions about any of the experiences that I've had that I share on this forum, or what we talk about, or even if you have a question about completion fluids which you we did not cover in this seminar, feel free to ask them, right? Now, beginning with completion fluids, let me tell you a fact. Completion fluids is by itself a complete what you can say is it's like a complete subject by itself. So it is so complicated to understand and really use completion fluids in the field, is that it takes years and years of experience to really build an understanding around this. It is fairly complicated, completion fluid design, and actually I can tell you that I have interacted with people who have already made a living for the past 30-40 years in the oil and gas industry only with completions. They are the champions of completions, and nothing else. They don't do drilling fluids. They don't have to do anything else. They don't know what rotary drilling is. They have made a career out of themselves only knowing completion fluids and only knowing what completion is. And I'll tell you why it is so important and why it can actually become a career by itself, right? To make it a career by itself, it's because it carries so much significance in delivering a well. So if you just imagine a well delivery process, right? The well is first found. Let's say that you do a seismic survey and you decide this is where I'm going to target, right? And this is where I'm going to drill to. And then you start designing the well, then you start drilling, you bring the rig, you start drilling. And after you drill, then you complete the well and then you produce the well. So every client that you work with or will be working with in the future, each and every client wants to produce the well. That is their main purpose, right? It's about making a profit. So they are running a business, they want to make a profit. So completion actually is so critical that it can make or break the well completely. Even if drilling is successful, that does not guarantee production. Okay. We are not talking about wildcat wells. We are not talking about exploration. We are not even talking about development wells. We are talking about all wells in the world, right? The completion actually is the key to the production of the well. And how you complete the well is all dependent on what kind of experts you have on your team and what kind of equipment you can access, right? So this subject is so vast that I cannot even cover it in 5 days, right? If I take a lecture for 5 days, I can't cover everything that I have to say about completion fluids. So what I have designed this lecture around is a few bullet points, few thoughts, and then you can go out and then, if you find something interesting, you read about it, you have questions, you come back to me. That's fine. And this can happen over a year, over 2 years, over 3 years. Feel free to connect with me whenever. But it is a thought-provoking lecture. It is just provoking you to think in a very different way. We've been programmed to think in a very specific way. Drilling is the master for success. I mean, if I know drilling, I know everything about the oil and gas fields. It is not really true. Actually, production is where the key of the entire oil and gas industry is. If you can't produce the well, drilling is of zero significance, right? So drilling is not the only industry that you can walk into. If you have good knowledge about geology and chemistry, you might as well make a career about how you deal with completions, right? So few bullet points and we leave it at that. So this is going to be an open lecture. It's not going to end. I mean, there is no end point for completion fluids, by the way. So I cannot end the lecture. I'll just give you the few bullet points and then you can think over it and read about it and research about it and then come back to me. So what we are going to briefly discuss is what type of completion actually happens in the well. And those completion actually then influence what kind of completion fluids you would need to complete the well. And then we are going to look at a few health and safety aspects of completion fluids, and then few displacement aspects and few corrosion aspects. But like I said, this is a very vast subject, and I cannot fathom to cover everything in one hour. It is impossible. So types of completions. Basically, what is a completion activity, right? It is very simply put together all the things that you do or all operations that are done to a well to make the well ready to produce, right? That's about completion. It's very simple definition, right? So there are different types of completions that you run in the well. Each has its own pros and cons. Now, like I said, I can't discuss each and every completion type because even discussing the pros and cons of each completion will take us a few days, a couple of days to go through. So I implore you to read a little more books which actually go into depth in making you understand why we choose cased hole completions in one portion of the world and why we choose open hole completions in the other portion of the world. And can I do open hole completions in in X part of the world, and why can't I do open hole completions in Y part of the world? So this is something that you will have to figure out on your own by reading the books that are available in your library or Google or wherever it is available, right? And there is a lot of material available to read about completions. So now the completion activity is actually broken down into two bifurcations, right? Two stages. One is drilling the reservoir, and then the other is delivering the reservoir for production. So completion activity being those two broad stages, the delivering of the reservoir or drilling of the reservoir is something which is very simple. It's like drilling a well, right? It's part of drilling a well. But then drilling a reservoir has its own nuances that we will discuss in a couple of slides later. But delivery and installation of completion hardware is the last stage and final stage. After that, you close the well and you make it ready for production. Then your production guys come in and then they open the well, they check for the well flow and stuff like that, right? So all that is done by the production people. But the final stage is once you install the complete hardware for completions, right? So there are open hole completions, then there are cased hole completions, and then there is gravel pack and packer fluids, and then there will also be workover. So workover is also a part of completion. So any remedial jobs that you're doing, any producing well that you have to shut down and do workover on to repair the well, to maybe tie back the well or stop the well from producing from reservoir A and start producing from reservoir B, open a reservoir on top or something like that, that comes under workover. So workover is also included in completion activities overall in the life cycle of the well. So case hole completions, as you can see by the name, is when you case the reservoir section and then you perforate the well. And now with your syllabus, I think perforations are covered quite okay. So you probably know what perforations are. So I'm not going to get into the entire depth of what perforations are, how they are done. All that can be read through your books. But cased hole completions are different from open hole completions. And these are the two broad categories of reservoir completions that we do. And then there are different stages to each one. You can either pump a open hole gravel pack, you can pump a cased hole gravel pack, you can pump production screen, you can have a production screen, you cannot have a production screen. All that is mix and match, right? So there are a lot of things that you will have to learn about completions. Now, what is a completion fluid? Because this seminar is all about completion. So the type of completions we covered very broadly, very superficially. This is not even 1% of the knowledge you actually need to become a completion engineer. But yeah, this is a thought-provoking seminar, anyways. So, what is a completion fluid? If you ask me, a completion fluid is as good as a drilling fluid. We've discussed drilling fluids for the past two weeks, and it has been well. I hope it has been well understood. So, a completion fluid is as good as a drilling fluid. But the only critical factor here is that a completion fluid deals with the reservoir. So everything is amplified. For example, in a common use, when you go home, right, you drink water from the tap, and you could drink water from a water purifier, right? So why would you drink water from a water purifier? It's because you want to be safe, right? Or you boil the water and then you cool down the water and then you drink a boiled water because you don't want any bacteria in your gut, right? Don't want to harm yourself. Now, water is just water, plain water. With naked eye, you probably cannot make the difference between purified water and non-purified water. So, you guys can still hear me, right? Yeah, yeah. Okay. So just checking. Thank you. Naked eye cannot tell the difference, but we know what the difference is, right? Chemically, there is a little bit of difference. If it's RO purified, if it's purified by boiling, we kill the bacteria. So it's all about what you put in your body, right? So you want to put in your body something which is more safer, right? So reservoir fluids are something similar to that. You want to put something in the reservoir which is much more safer. And what is that safe? We will discuss a few points here in this seminar. But it has to be safer. It can't be a normal drilling fluid, and cheap and dirty drilling fluid will not work in a reservoir, right? It certainly can in few cases, and those are very seldom cases, right? If a cheap operator wants to drill the reservoir section with a drilling fluid, he incurs a lot of formation damage. Now, we are going to discuss formation damage, although very superficially in the seminar, but there can be massive amounts of formation damage if the reservoir fluid is not designed properly, and that will hamper your production. So basically, all the money that you have spent through in drilling the well, in making the reservoir and starting to produce, can be all lost in the well, right? So workover fluids are used for workover operations, and completion fluids are used for completion operations. But these are just terms that are used interchangeably. So a workover fluid can also be a completion fluid, which was used in the completion of the same well, right? So both fluids could be the same. Their properties are also very similar. So don't get confused. Workover fluids are not necessarily something which is very separate from the completion umbrella. So completion fluids is a broad umbrella which has all these packer fluids, all these breaker fluids, and everything inbuilt into it. So completion fluids is a very broad category. Now, clear brines, and we will get into the technical terms in a few slides from now. But clear brines are mostly chosen to do reservoir completions, and I'll tell you the reason why in a few slides later. But just remember what it is. It is just pure salt and water. So if you make a sodium chloride brine, you can make it at home. You can just take common table salt and you can pour it in water and you can mix the two, and that becomes a sodium chloride brine in technical terms, right? So clear water and any kind of dry salt mixture is called clear brine, right? You don't add any other chemical to it. Then it is classified as clear brine. Otherwise, it is classified as completion fluid. So that is the major difference. Now, the biggest, if not the most important property that you need when designing a completion fluid is that it should be stable at both downhole and surface conditions. And I'll tell you why I say that in a few slides later. You will understand what is the real chemistry behind why I say that it has to be stable at downhole conditions and as well as surface conditions, right? So just for now, keep it in mind that this is the common primary requirement for a completion fluid. It has to be stable on the surface. Like if you hold it in a cup in your hand, it has to be stable in that. And it has to be also stable at downhole temperatures, which could be 400 degree Fahrenheit or 200 degree C or whatever, right? So I hope with your geology background, porosity and permeability and how they are interrelated is very well understood by you. And everything is now, when you talk about the reservoir, everything is porosity and permeability related. That's where your key problem and key solutions lie in porosity and permeability. So if you are adding something from the outside, which is could be a reservoir drill-in fluid or could be a completion fluid or whatever, is actually going to change the properties of the reservoir. It is going to change the porosity and permeability. And if the natural porosity and permeability of the rock changes, of the reservoir rock changes, that means production it could be hampered greatly. Now, I hope the dots are starting to connect now. Why the completion fluid design is so important. So any permeability reduction should be avoided. This is a general term, but remember that it cannot be avoided 100%. So there will be some kind of damage to the reservoir, 100%. No matter what fluid you use in the world, there will be some type of damage. Now, all formation damage cannot be avoided, but has to be minimized in technical terms. So technically and economically, I could use, for example, I could buy a Mercedes Benz and use it every day. But is it going to be economical? Maybe not, right? So I maybe use Mercedes Benz only over the weekends and then use a Maruti Suzuki Swift or whatever on my everyday commute. So economics has to balance, right? I could really take the best clear fluid brine in the world and be bankrupt completely, right? For example, I can give you a very good example in the oil and gas industry. ONGC used something called as the cesium formate brine. Okay, so just to give you a background, cesium formate is the world's most costliest clear brine that you can buy. 1 barrel of it costs about 6,000 US dollars. 1 barrel. Okay. So 6,000 US dollars, that is without anyone's profit. That is the bare minimum cost of the brine. Then there will be transportation costs and etc. 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 So cesium is a radioactive material, but cesium formate could be formed in salt form, and that is a very heavy density brine, that world's heaviest density brine that could be used in oil field applications. There are other brines that are available, but we can't use it because for the sole reason that they are radioactive, right? So cesium formate could be used, and 6,000 US dollars a barrel. So do I spend 6,000 US dollars a barrel, or can I really work with sodium chloride, which is common table salt? So one barrel could cost me what, 30 US dollars, 40 US dollars maybe to make with water and sodium chloride. So the economics has to work out. If I have oil which I have a very large reservoir, for example, and it's going to offset the cost of using cesium formate, and the well really demands it, then yes, I will go for cesium formate. But if I don't have a reservoir which is big enough, which is large enough to produce, then no point in using cesium formate. So it has to be economically making sense. Technically, I can do whatever I want. So economics has to also make sense. Now, where does the damage occur to reservoirs, if you ask me? So simply said, it occurs from the solid material you use and the filtrate material that enters the reservoir rock. Now, we spoke about filtrate quite a bit in the last seminar we did when we were talking about rock fluid interaction. So remember that the filtrate consists of chemicals as well, which it takes inside the reservoir with itself. So those chemicals could damage the reservoir permanently, and irreparable damage. You cannot reverse it in certain cases, right? So that's why the design of a reservoir fluid is very, very critical. Cement also damages the pore networks, which is, I think, self-explanatory. So your understanding of the porosity and permeability of the reservoir rock is very, very critical. So a few damage mechanisms, right? And let's look at it in a symbolic way. This is very simplified. It is not actually happening exactly like this, but this is a little more simplified for you to get a visual representation of what could happen. So we'll start on the extreme left and then move towards the right. On the extreme left, you see two fluid pictures, right? Two jars, right? One jar is like mildly whitish, and the other jar is completely transparent, right? Like a mirror. So just imagine both of them as reservoir fluids, and which one would you pick? You don't have to answer it right now, but I hope towards the end of this presentation, you will be able to answer it for yourself. Whether I pick the one which is like milky white, which has some solid particles suspended in it, and that is trying to make it a little turbid in nature or a little dirty in nature, or should I go for the one which is like a mirror, just transparent, right? On the middle picture, you can see emulsification damage, right? So if I have a filtrate which is completely oil, that may look black, right, on the extreme left-hand side of that second picture. And then on the extreme right-hand side, you can see a very significant separation between oil and water. So which one would I like in the reservoir? Depends on what type of reservoir it is. A reservoir could be oil wet or water wet sand, right? If you're producing from sandstone or shale or whatever, it could be oil wet or water wet. So do I want water and oil separation in a water wet reservoir? Or can I live with oil in an oil wet reservoir? Those kind of questions have to be answered with a completion fluid. So a completion fluid is simple design. I used oil-based mud to drill my well. Let's use an oil-based mud reservoir drilling fluid, and no problem. I mean, I can, if I can use it for drilling, why can't I use it for reservoir? Not simple like that, right? It's not as simple as that. It depends on the reservoir rock as well. So oil wet sandstone, and I'm talking about the picture on the right side for you. Let me get a laser pointer, it will be easier. All right, so in this picture, you could see that oil wet sandstone. If I have a situation like this could really mean a disaster for this sandstone reservoir. If that separation of water and oil happens on the filtrate in the lab, and I still pump the same fluid here in the reservoir, I will have a massive problem in producing from this reservoir, because there will be water droplets which will cause a water block for the production. Now, on the reverse side, if it's a water wet sandstone and if I have the same oil, 100% oil going in, then I have an oil block and I won't be able to produce oil from. That's why the chemistry and the geology has to interact with each other. They need to know both sides, which is well suited for our kind of syllabus or our kind of students, because they know how to make the connection. So here is a graphical representation of what we are trying to do, right? And the fluid selection actually means what is the reservoir characteristic. That is the first benchmark, right? The exact first step that you take before you decide a reservoir fluid or reservoir drill-in fluid or a completion fluid is you need to know what is the reservoir and what is the reservoir characteristic. If it's oil wet, it's water wet, it consists of a gas. The main production is gas or main production is oil. What kind of oil? Is it thick oil? Is it light oil, or what kind of API number it is, etc., has to be known very well, right? Before you make a selection. Now, drilling fluids and reservoir fluids, like I said, share the same characteristic. Actually, if you see the mud report, it will look the exact same. And sometimes you may be just puzzled. How is it possible? This guy is selling me drilling fluid at $60 a barrel. And now it is trying to sell me a reservoir drilling fluid, which is $100 a barrel. Why should I pay twice the amount of money if they are giving me the same characteristics on a mud report? well, my friend, the interaction between the reservoir and the reservoir drilling fluid is quite different. And that's why it is pumped with a special blend of chemicals, right? It's not regular chemicals that you use to make the reservoir drilling fluid. And then you have to understand what is the reactivity of the shale if you are dealing with shales in your reservoir. In any kind of clay in the reservoir, that reaction has to be well known. So, what is the mechanism that could occur if I have a very high reactive shale? If I put a water-based mud into it, what will happen? It will swell. It will make the reservoir inaccessible to our completion equipment. And what case will happen after that, right? We may lose the entire well. So those kind of small little things have to be known before you start selecting or making up your mind as to whether I'm going the oil based route or whether I'm going the water based route. So one barrel of water-based mud and one barrel of oil-based mud, we've looked at what are the chemicals, right? We've looked at the chemicals already. But now there is a different selection when it comes to reservoir drill-in fluids. So reservoir drill-in fluids, RDFs, are the fluids that are used to drill the reservoir. And you can see that basically we're trying to avoid using barite as much as possible, because barite is a very difficult material to get rid of in the reservoir. It is not acid soluble. So even if you pump the world's most toughest acid in there, barite will not dissolve. So you cannot treat out the barite. So once barite enters the reservoir, the only way to treat it out is by flowing the reservoir back. So that barite will come with your crude. And would you like any kind of adulteration in your crude when it is producing? No. Crude should be produced 100% crude. You don't like water mixed with it. You don't like gas mixed with it. You don't like any kind of foreign material mixed with it, because that will add to your processing costs. So crude, once it is processed, it distillates into many different things. I think you probably know the process by now. So we want minimum adulteration to the crude that we produce. That's how clients make money, right? So they want to avoid using barite as much as possible. So they use calcium carbonate instead. What is the biggest advantage of calcium carbonate? Now, this is a question for you, right? So you can discuss it amongst yourselves and you can understand why calcium carbonate is used, because by nature of what calcium carbonate is, there could be a reaction that is much more feasible to be used in reservoir drilling fluids, right? So that's something of a homework for you to, figure out why calcium carbonate is being used instead of barite. So how do we select a completion fluid, and what is a completion fluid? Like I said, a completion fluid is a mixture of, generally speaking, a completion fluid is a mixture of dry salt and water, right? So whether I use, what kind of salt should I use? Should I use sodium chloride, because that is the cheapest material that I can get? Whether I should use calcium chloride, or whether I should use some other kind of salt like cesium formate, like I said. So those things are decided by what density I require. Like I said, fluid density, fluid density, fluid density. Density is something that you cannot avoid. Density is the core of drilling fluids, and is also core of reservoir drilling fluids, and also the core of completion fluid. Never forget the density, right? Density is actually the basic. It's as good as walking. Like, you know how to walk, you learn how to walk as a kid, and you walk all your life, right? Until you pass away. So it's as basic as that. Density has to be everywhere. Now, after that, it is the bottom hole temperature. So a bottom hole temperature of 200 degrees C versus 100 degrees C versus 50 degrees C, all can be handled very, very differently, right? From a single salt, or also use some different kind of brines, right? So we will look into what kind of brines are available in the market. Also, you have to look at the coldest temperature to be encountered. And now, why I say that is because go home and you can possibly do an experiment, or maybe go to your chemistry lab and do an experiment. Dissolve some table salt in water and try to recover the salt back again by cooling that mixture and see what it does. So it's basically water and common salt, and if you cool it down, what is the temperature you need to take the first crystal out of salt, right? The first crystal of salt out of water, out of solution. What is that temperature? You can find out, right? So you need to be aware of the coldest temperature. I cannot take a brine or a clear water brine that works in, for example, in India. The same could work in Russia. No, because Russia has colder temperatures, right? The one that works in India could probably work in Malaysia because similar temperatures, right? Tropical climate. So you need to be aware of the climate as well. And what is the compatibility with the completion method? So we will look at corrosion, very, very basic types of corrosion, and what is corrosion, and that's where the compatibility is, right? Remember, I think you have a subject called directional drilling and you're learning about directional drilling. Remember that all these tools that you're using downhole have rubbers, or they call it elastomers in technical terms. These elastomers react very differently to different kinds of completion fluids. So if I now have a completion string design where I have these elastomers, and if one of these elastomers is going to get damaged just because I use X type of fluid and not Y type of fluid, it will be very detrimental if I still use X type, right? So you need to understand exactly what kind of things you are using to make the well complete, and what kind of elastomers, what kind of plastics, what kind of metal. All these things really weigh heavily on the selection of the completion fluid. Now, the completion fluid is then divided up into stock fluids and spike fluids. Stock fluids is very simple. You take a salt and water and blend it together to make a stock fluid. Now, that fluid could also come in a liquid form. So basically, you are not mixing it on the rig. You are just buying it on the shelf, pre-mixed by someone else. That's option number one. Option number two is you can mix it dry and dry powder and water together on the rig side. It's still called a stock fluid. And now spike fluids is something which is very, very heavy. The spike fluid is basically always pre-made and sent on the rig side to make it simpler. The operations are made simpler by that, right? So stock fluids and salts, I've given you a very brief idea. These are not all the salts that the oil and gas industry uses, right? So remember that these are not all the combinations that you will use, but these are just the most used ones, right? There are some unusual ones also, which are available in the market, but I have not tried to cover them because it will make things very complicated. But remember that there are monovalent ions and then divalent ions. Go back to your chemistry lectures that you have done back in school. Monovalent doesn't go with divalent. They don't like divalent, right? So don't mix them together. So it's like two people who don't like each other, and if you put them in the same room, they will end up fighting. So these guys will end up fighting with each other. So never do that, right? So design is again whether I want to design a monovalent ion clear brine or a divalent clear brine, and then you stick with it, right? So everybody has their pros and cons. Like I said, tropical climates and cold climates are something that you will see, and I will explain why these are so crucial for you to understand. When it is just salt and water, how complicated could it be? I can make this at home if I want to, right? I can just buy salt, टाटा नमक खरीद के लाओ और उसको पानी में डाल दो. That is sodium chloride brine, right? I can make sodium chloride brine all day long in my school, my college, my home. So why is it so complicated? Why is Rahul speaking like as if I don't know how to make sodium chloride brine? It gets very complicated because it is a large application and how you are applying it. So for example, if I do the same sodium chloride brine in Russia, that it's not going to work at the same density. If you notice the first two lines in the table, I can make a 11.6 ppg brine in India with the same salt, but I can't make it in Europe because of cold climates. I can only make 11.3 maximum. So one size doesn't fit all. If I work in India, it has a different tactic, and then I go to Russia, it is going to be a very different tactic. It can't be the same thing, right? You need to understand the difference. Now, I've given you a brief idea of what are the typical density ranges, right? So if I need a well needs about 11.8 ppg, then I can probably use calcium chloride, right? But if it moves over to 15.3 ppg maximum, then I'll have to use calcium bromide, right? So these salts are of different grades. First, second, not only different ions, but of different strengths. The ionic bond are of very different strengths, right? So these bonds can be broken in certain scenarios, and that could lead up to a big problem if I have a very high temperature well, for example, and I put calcium bromide in it, right? And God forbid if I have not thought about the bottom hole temperature, right? Being very hot. This calcium bromide can actually give off bromine gas. And bromine gas is very detrimental to the steel, the type of steel we use in our oil wells. The casing will collapse. It will erode itself off and the casing will collapse. These kind of things have happened in the past, right? Very old past, not in our generation, but very old past. It has actually happened. So that's where the learning comes from. That's where the criticality of the design comes from, right? Which it's not only about the density; it's also about the bottom hole temperature. So many factors are coming together, right? So a few things that you'll have to keep in mind before you select a certain clear brine, right, or select a certain kind of completion fluid. So one is density, like I said, but density is not measured in the regular way. If you remember the last seminar we did, you remember the fluid density. The guy was measuring the fluid density on the rig site, and it was a mud scale. We don't measure completion fluids on a mud scale. It can't be measured on the mud scale. It is measured by a hydrometer, right? Go to your chemistry students or chemistry classmates and ask them what is a hydrometer, right? And they will explain the exact physics, what is the hydrometer and how it is used. So this bottom picture actually shows you how you do it in the field. You take a test tube, you fill it up with your clear brine, and then you drop a hydrometer in it, and then you measure the weight. So basically, it is the weight of the fluid and not of the dissolved particles, right? So these clear brines actually take up a lot of unclear particles also, particles which could be suspended but not dissolved. So the dissolved part is the only density that the well sees. The undissolved part, the density could not be seen, is not seen by the well. So when you talk about overbalance, you will have to look at the dissolved portion, and that's why the hydrometer is used. Now then there is something called as the true crystallization temperature. You remember when we spoke about cold temperatures and cold temperatures requiring different salts or not requiring the same densities or not acquiring the same densities even though I use the same salt and same water combination. It is because of the true crystallization temperature. So salts will crystal out of solution at certain temperatures, and if you reach that temperature and God forbid if your brine is saturated completely with the salt, the crystals will start forming, and if these crystals start forming at the bottom hole, at the bottom of your well, you are in big trouble. You can't actually get rid of these crystals. Once they start forming, no matter what amount of water you pump in the well, these crystals will not go away. Okay, so it's that bad. It will lock up your entire well. You can't suspend the well. You cannot operate your BOP. There are times which has actually happened. You cannot operate your BOPs. Your BOPs will get stuck. So basically, the rig is just stuck over there, and you can't do anything, right? So true crystallization temperature, or TCT as they call it, that's phenomenon well known to our chemical brothers. So you can go to your chemistry department and understand what is a true crystallization temperature and how it is measured, and it's very basic. So those things really matter very heavily on what kind of fluid you will be using. Then we have already spoken about pH, so we are not going to discuss that here. Solids content. With reservoir damage, solids content is something that you pay a lot of attention to. If I have solid content 1% by volume, or 10% by volume, or 30% by volume, it makes a massive impact on what kind of quality of a reservoir I'm delivering for production. So solid content is always measured. It is more critical during your reservoir section. It is not as critical as in the drilling fluid section. So the range of tolerance of solid content is quite wide and starts getting narrower and narrower as you go towards your reservoir. Turbidity. So we spoke about this milky kind of solution, and then there is a very clear solution. We always want a clear solution in the reservoir. Whether we achieve it in the reservoir, yes or no, that is up for debate, right? But a clear solution is what we prefer. So NTU meter, which you see right here, is used to understand what a kind of turbidity is in my brine. Turbidity is basically what it is doing is it's taking a sample from your active pit or your flow line or wherever, and then inserting it into this meter. It's called a nephelometric turbidity meter, or NTU meter in short. And what it is doing is actually, when you press a button, it throws a laser across this bottle. This bottle is like a glass bottle. So it throws a laser, and then the laser diffracts. If there are solid particles suspended which are not dissolved, it will refract the laser. So those light lasers which are refracted are then measured, and then you see what is the nephelometric turbidity unit. So the higher the number on this display, the more turbid your clear brine is. And by the name clear brine means it has to be clear. So there is always a tolerance limit that is set up. So sometimes they say less than 100 is acceptable. Any more than 100, you have to go filter the brine. Filtering the brine is as good as making tea. When you make tea with the tea leaves, dried tea leaves, you filter the mixture, right? You boil it, you filter the mixture. You don't drink it with the tea leaves, right? So it's the same thing. You make it non-turbid by filtering it through filter paper, just like how you do for the tea. So it's very simple, but very complicated operation when you look at the grand scale of things. It's not a tea, maybe is just 250 milliliters. This we are talking about 10,000 barrels, 15,000 barrels, right? There's quite a bit of difference on the scale of things. And then there is the water activity. So we are not going to discuss water activity because water activity is a very complicated subject. Very easy to calculate, but very complicated to understand. So go back to your chemistry books and start reading about what water activity is. What is the water activity in your tap? What is the water activity in your RO purifier? What is the water activity of a brine, right? What is the water activity in the well? What can I sustain? Those kind of things are very crucial to understand before you proceed with the brine in the well. Now, there are some hazards also associated with this brine. And why am I talking about hazards? Because the hazards associated with brines or their salts are much more significant and very aggressive in completion operations than when you compare drilling fluid operations, because drilling fluid operations are pretty much very safe apart from the point where there could be a well controlled situation. In completion fluids, the hazards are a very wide range. I mean, your skin could get burnt. You can lose the skin of your hand or your feet, just completely over. I mean, your bone. You can be stripped to your bone just by dropping some kind of acid on it. And I think you probably would have seen it. So completion operations actually go hand in hand with acid pumping also. There is a lot of acids that are pumped as breaker solutions to get rid of reservoir damage that is done by RDF and completion fluids. So that could get on your skin and damage your skin. Now, since we're talking about brines and not really acids or acid jobs, we are focused on brines. Remember that some kind of salts actually react with water and are exothermic, right? So you can go to your chemistry lab and ask about what is an exothermic reaction, or maybe we have some kind of calcium chloride salt in the chemistry lab, and just pour it in water and try grabbing the beaker where you mix it, right? It's very hot. It will get very hot, right? So in these kind of scenarios, you need to know which salt reacts how as a basic reaction. And if it is an exothermic reaction, you have to take precautions, right? Now you're going to tell me, Rahul, I mix calcium chloride, and I've heard calcium chloride brine is a very regular occurrence in oil field. I mean, you use calcium chloride brine in oil-based mud. You use calcium chloride brine as brine in water-based mud also. So this is like a regular activity. So why you are cautioning us so that this is very dangerous? It is very dangerous because you don't know how to handle it, right? With oil field, we know, with the experienced guys, we know how to handle it. So I'll give you an instance what has happened in the past. So I was working in Kakinada. Of course, I was working for Slumberjay at that point of time, and I was in the mud plant. For those who don't know what a mud plant is, it's like a place where you do offline rig activity, offline drilling fluid mixing, so that the rig can save time. So we mix things in bulk and ship it off to the rig, either offshore, onshore, however, by trucks, by boat, whatever. It doesn't matter. So we do bulk handling, bulk as in large quantities. So this was a new mud plant made, and I was a day shift guy because I was senior. So our junior was a very new guy, and generally when you do shift change, you make a handover. So I make a handover. Hey, mix 200 barrels of calcium chloride brine and keep it ready for the morning, so I can come back and mix some drilling fluid with it. This was the instruction that I gave, and I left. As soon as I reach the staff house, I get a phone call from the same person who I handed over. Sir, there is a problem. I need you immediately in the mud plant. So I say, okay, are you hurt? He says, no, I'm not hurt, but somebody is going to get hurt very soon. So you have to come immediately. So I rush back to the mud plant. 15 minutes later, I reach the mud plant. And what I see is mind-boggling, right? It just blows your mind away. I have 6 by 6 feet of and about 10 feet high mud tank made out of pure steel, right? Very thick steel. I mean, those tanks are heavy-duty tanks, right? That tank is moving as if it is made out of plastic. It is like a jello. It's moving on its own. It's like jelly. The steel is like jelly. How is it happening like that, right? What has actually happened is while mixing calcium chloride salt with water, there is an exothermic reaction. Now, if there is a reaction which is exothermic, and for people who are unaware of what a exothermic reaction is, exothermic means it gives off heat. So if I don't give that heat an outlet to go away, that heat will turn into steam and it will circle inside the tank as if it is like a bomb, and it will start making pressure, right? It will start creating pressure. So this person who I had asked him to mix calcium chloride brine was unaware that this is an exothermic reaction, could cause a lot of heat, and he has to keep the lids of the tank open so that the heat can vent out. If the heat doesn't vent out, the gases inside will build up and will make steel hot. And if the steel becomes hot enough, it will start behaving as if it is malleable, and the rotators or the agitators that we call inside the tank are still on. So just because it is moving with the agitator, the fluid is moving with the agitator, actually you can see it outside from the steel, the way the fluid is moving. And a solid steel block is moving like that because of the exothermic reaction. So it can get hot. It can get so hot that it can burn you, right? So you are supposed to be aware of these chemical reactions. It's more chemistry, right? Very, very basic chemistry. Now, some salts, on the other hand, actually make things colder. So, potassium salt, for example, potassium chloride is readily available in the market. You can make this experiment at home if you want. Take some potassium chloride, put it in water, and dissolve it. The water temperature will drop. So water temperature can go below room temperature and become cold. If that happens, what happens to things that you put in steel? The steel will, from the outside, will start making droplets, because if it is cold, it will start gathering moisture as droplets on its surface, right? So you have to be aware. You can't be surprised once you are asked to mix this kind of fluid on the rig site or in the mud plant, right? In bulk. Some salts are very hygroscopic. Hygroscopic is water loving. They will actually pull moisture from the air and become wet. So if these salts are put outside in the warehouse, these will start becoming like water. They will start pulling moisture, dissolve in water, and go away, right? So or they will become hard like rock, and you will be having a very tough time to mix it. So you have to be aware of the nature of the salt that you're mixing. Now, chlorine and bromine gas, we've spoken about this already. Oxidizing agents, or agents which actually oxidize on the rig side, are commonly used as breakers or acids in your acid job. So to make the acid more aggressive, you add an oxidizing agent or a reactant with oxygen. So in that scenario, these things will actually make your life miserable. Oxidizing agent is something which will, if you breathe, you will have a problem. You will feel short breath if you breathe in. So there is a scenario where I had asked someone to mix an oxygen scavenger. By the name, you probably understand what an oxygen scavenger is. It actually takes away, it reacts with the oxygen in the air. It takes away the oxygen and creates something else, right? So let's leave that part, what that something else is. But an oxygen scavenger, if you smell the oxygen scavenger, what will happen? It will scavenge the oxygen from your lungs. It can actually become a gas, travel to your lungs, scavenge the oxygen from your lungs, and actually make you, it can kill you if you have enough exposure to it. So this roastabout is new, and I asked him to mix some oxygen scavenger. And just because the smell is really bad, what he does is he puts his nose and he takes a big smell of that chemical, and then he collapses. He just collapses on the rig side. Everybody is alarmed, and the doctor comes in, puts him on an oxygen ventilator. He survives. He is not damaged, right? But these kind of things can happen. So you have to be very mindful of what you are doing when you're dealing with chemicals, right? All right, now the chemical part is done. Now we are going to only talk about two more things which are briefly involved in a completion fluid. One is your displacement of the completion fluid, and second is corrosion. And then we end the topic. Like I said, I can't do everything in 1 hour, and this is a subject which could take easily 5 days, and we still won't be done, right? So when you talk about displacements, this is an art. A displacement is actually an art. It's like your mom's cooking. No matter you write the recipe down to the single letter, what your mom is doing, right? Is try to replicate it yourself. You can't, right? Sometimes. So displacement is simply an art. You only learn by doing, right? So displacement actually is of many types, and I have just classified between indirect and direct and forward and reverse. But you can read displacements is a very complicated endeavor. It's I can take 5 days, 10 days to really do displacements in depth, but we don't have that much time. So displacement is actually what we are trying to do is take one fluid out of the well and replace it with the second fluid. It's simply that. If anybody else tells you something else, is wrong. In essence, you are trying to take one fluid out and put the second fluid in to maintain the hydrostatic pressure. But it can get complicated when you do oil-based to water-based mud displacements, water-based to oil-based displacements, water-based to water-based displacements, water-based to clear brine displacements. All these things can get very, very complicated. So before and after picture that you see on top, you can see very well if I have an oil-based mud in the well on the steel pipes and everything, if I start displacing, what I want it to look in the after part is very clean. Do I get it? That is a design of the cleanup. It's called the cleanup, right? So how do I design a cleanup is what is going to make the before and after image. If the after image is like the before image, then I have failed at my displacement completely. So what we use is a triple three-pronged approach. One is the mechanical way of cleaning everything. Then it's the chemistry of the fluids, the volume, the turbulence that you create, the flow pattern that you create. It is very, very complicated. I mean, you can write research paper after research paper only on just displacement. Forget about the chemistry, forget about everything else. Just the displacement of a well, you can write research papers after research papers. It is still a very very non-understood subject, right? It's that complicated. And then there is hydraulics, like I said, the flow patterns, the what is the velocity in the annular, what is the velocity inside the drill pipe, what is outside the bait. All those things are calculated to the last decimal to understand what the fluid will do if I start displacing fluid A from fluid B, right? And if fluid A mixes with fluid B, then it is a catastrophic failure, right? The well does not only have steel and fluid, it also carries so much debris. Just by the drilling activity, it carries so much debris. These are actual pictures of the things that are collected outside from inside the well, right? We run magnets. There are large magnets run. So your tools, the rat hole and the drill hole is always covered. You can see it. They tell you not to take any tools very close to the wellbore. So if you ask me, what if I drop a small nut inside the wellbore? How does it matter, right? Because the well is 8 inch, and if I drop like a small nut, what is going to be the problem? There is not going to be a problem. Well, there is a big problem. That nut is not where it belongs, right? It can get stuck in one of the nozzles, and your bit nozzles will get hampered. Your bit will stop functioning. You can have a trip out, right? A trip out in a deep water well could take about 8 hours sometimes, depending on what depth you are. So you will be effectively losing 8 hours of drilling time. 8 hours is $8 million, just rough mathematics, right? So who will get blamed? So these kind of things are very, very critical. We have to be very mindful when you are around the well. And the last, very simplified, corrosion, right? Corrosion basically is an electrochemical reaction, and I think everybody knows what corrosion is. But in oil field terms, it can make or break the well, right? It is as simple as that. People have spent their whole lives becoming corrosion experts and actually made a career out of it. So if you go out and you say I am a corrosion expert, people will pay a top dollar to get you on board, because that corrosion expert can save them wells which are already damaged because of corrosion. They can also prevent any damage in the future, right? So you will get top dollar if you are master of corrosion. Yeah. So electrochemical process, we know how much damage can it make. Let me show you a few pictures. So this is the damage that a corrosion can make. If left unattended, this is inside the well. It can actually break the pipes into two. This is a pipe which is broken from the inside, right? So there are different types of corrosion, and I'll request you to go ahead and read on your own what these different types do, how do they look, what do they do, what is their entire mechanism. It's not all of them are electrochemical reactions. Remember that forever, all of them. But there are different electrochemical reactions happening on each and every one of them, right? So just by knowing the types and what they do, we probably can prevent them. There are chemicals which prevent these types. So if I have H2S in the well, I need to look at sulfide stress cracking. I need to do that, right? And I need to use things which are actually mitigating that sulfide stress cracking, right? So those things have to be taken care of in the chemistry, in the design of a completion fluid. All right, so this is the end of the workshop sessions. I know that I have left you a little bit of lost, a little bit of confused, but that is the whole purpose. It's to invoke the thought process. It's to invoke you to read a little bit more outside your own syllabus. Spend some time to explore, because nobody is stopping you from exploring, right? So get the answers for yourself. If not, then ask the questions, and then I will be more than happy to answer them for you, right? So with that, I will end, and then we will start taking questions.
Thank you so much, sir, for such enlightening lecture. Now I request students to put your names in the comment box if you have any questions. So we have one question from Sumedh. Is there any difference between perforation in a liner and a production tubing?
Very big difference, actually. A liner is actually hung or could be cemented to the wellbore wall. Okay, and perforations in a liner is a very different thing. I mean, once you perforate any liner, it gives you access to the reservoir. Now, production tubing is very different. Production tubing is what connects the well, connects the bottom of the well, or wherever you are trying to recover oil or gas from, to your equipment, which is on top, which is into your Christmas tree, and then the Christmas tree or the pipeline or wherever it goes, right? So those two are two different things. They are not interrelated. Perforation in a production tubing is very different. Very different mechanism. They're not interrelated. They're not interchangeable, right?
Thank you, sir. Now, Harshal, you can ask your question.
Good afternoon, sir.
Yeah.
Sir, my question is, like, how do we prevent losses in case of brine?
Good question, Harshal. Actually, very good observation. Loss prevention in brine is a very, very complicated scenario. In simple terms, I'll tell you that polymers, we use very different chemistries to pump inside the wellbore, which can stop the loss circulation only for the time being. There is no permanent solution there unless you cement it or case it, right? Case it and cement it. There's no permanent solution. We do impermanent solutions only with brines.
Okay, sir. Sir, I have one more question.
Yeah, go for it.
Sir, like you mentioned about cesium format. Sir, can cesium format used as drilling fluid?
It can be, Harshal. It can be used as reservoir drilling fluid. It can be used as drilling fluid. It can be used as any kind of fluid, right?
Okay.
But the question is, do you want to spend money on it? And that's why it is not widely used.
So, sir, cesium format is like solid free mud. Some people will say that it is solid free mud.
Yes, it is. It is.
And in high temperature and high pressure well, will it be useful to, or means can we more precisely use cesium format there?
Actually, you can use cesium format in every well in the world, right? Which is being drilled right now. It is very simple like that. Okay. To answer your question, you can use it in every well. The problem is the cost, right?
Okay.
And what is the trade-off? So there are certain things that you trade off. I can use cesium format in every HTHP and deep water well in the world. Okay, every HTHP and deep water well in the world. But do I really have to use it, or can I use something which is much more cheaper but get the same well delivered to me, right? That's the question.
Yes, sir. Sir, and one more thing is like, how do we prevent wellbore stability while using brine?
You mean wellbore instability while using brine?
Yeah, wellbore instability.
Okay, so wellbore instability in brine is a very different maneuver. You use a physical, what do you call it? You use an understanding of physics and chemistry to really do that. So how a clear brine without any suspended particles can strengthen a wellbore? It can't happen. So you can use some dissolvable polymer which can temporarily stabilize the well, right? So like I said, the design is very, very complicated. It's not a very simple answer to give, but it can be done. 100% it can be done. There is no question about it. It's just a matter of how you design it. And there are a few chemicals that you have to work with. So, which don't damage the reservoir for sure. They don't damage the reservoir. So, yeah, it can be done.
Okay, sir. Thank you so much.
Thank you, sir. Prajwal, you can ask your question.
Good afternoon, sir. My question is what we are currently using in drilling mud to prevent the corrosion.
Okay, Prajwal, very good question. Corrosion in drilling fluids and in completion fluids are two, I can say they overlap in some cases, right? Some cases, there are some chemicals that you use both in drilling fluids and in completion fluids. However, remember the drilling fluids have so many chemicals mixed within it, and it's constantly moving, right? It's constantly being circulated in and out of the hole. So in that scenario, and especially oil-based mud, corrosion is almost unrelated, right? Corrosion almost never happens in oil-based mud. electrochemically. Okay, remember, electrochemically, it will never happen. With stress-related corrosion, it can always happen with oil-based or water-based. It doesn't matter. But when it comes to completion fluids, it is much more enhanced because it is only a mixture of 2 or 3 chemicals. It has no other buffer that can really work in its favor to stop corrosion. So corrosion is much more amplified in brines. So that's why it requires a lot more attention and a lot more design element to it when you compare it to drilling fluids.
Okay, sir. Thank you.
Thank you, sir. Rahul, you can ask your question. Rahul, please ask your question. Okay, so maybe he lost his connection.
No problem.
So moving
Is there
forward,
any other question? Maybe he can email it to me or email it to you and you can forward the email to me.
no, Rahul, you're not audible.
Maybe he can type the question in the chat box. That's fine.
So we will wait for 2 minutes.
Okay, Rahul has posted his question, and for the benefit of the crowd, I'll read it out. If we are drilling in our reservoir and our pores are getting blocked by solids from our mud, and we want to treat it with acid, so how do we know our acid will not affect our formation? You'll have to test it in the lab, Rahul. So a breaker design or an acid design happens way before you actually pump it in the well. And you can test it against the reservoir rock to find out what is the impact. So in certain cases, the impact is always there, but you can sustain the impact by just changing the design or lowering the strength of the acid, or all that tweak happens in the lab. So every design is unique to itself. All these acids and all these breakers don't come as a one size fits all. So it doesn't come in liquid form in one container and you just pour it in the well and it reacts. It is not like that. Every well could have a very different design and very different strength of the acid. I hope that answers the question.
Thank you, sir. Thank you so much, sir. We are eagerly waiting for the next interactive session. Leading to the end of this session, I call upon the treasurer of our student chapter, Mr. Sahil Phadtare, to convey the vote of thanks.
Thank you, Abhishek. Now, good afternoon, everyone. First and foremost, On behalf of Navroji Wadia College SP Student Chapter, I express my heartfelt vote of thanks to our speaker, Mr. Rahul Day. The 3 days workshop has been very informative and useful. Thank you for taking out time from your busy schedule and gracing us with your knowledge and guidance. I would also like to thank our faculty advisor, Mr. Sagar Thakurdas sir, for making it all possible. Finally, I would like to thank all the participants for attending and participating in the lecture series and being such an attentive audience. Thank you, everyone.
All right. Thank you, everyone, for the attendance. I hope it was slightly beneficial for you, or I have added a bit of what you call it, a bit of curiosity to your knowledge, so that you can go seek out more clarity on what you want to do in the oil and gas industry in the future. I have emailed Sagar already the PDF copies of all these three workshops that we did in the morning. So I suppose that he can distribute it onwards to all you guys individually or in a group email, however he chooses to use it. Apart from that, yeah, I am available to answer any questions whenever they arise. Feel free to email them to Sagar, and he can reach out to me on one email, so that it becomes simplified for me instead of me answering 15 separate emails. Yeah, good luck, everyone. I suppose you will be entering your exam semesters very soon, so good luck to the people who will be sitting for exams. Don't feel disheartened by whatever is happening around you with the green revolution they are talking about in the oil and gas industry. The oil and gas industry is here to stay. It will stay for the foreseeable future. So, for example, me, I am what, 36 years old, and I'm not planning to retire anytime soon. So, with that, I am planning to continue in the oil and gas industry. This industry will survive another 20, 30 years easy. So your careers can be made in oil and gas. Don't worry about this green revolution. This is just statistics that people want to put through so that they please the governments all around the globe. Things will change. I'm not going to say that they won't change. They will change for the better, but that does not mean absolutely that you won't find a job. Maybe in a different, you won't be a drilling fluid engineer. You could be a green drilling fluid engineer or a environmentally friendly drilling fluid engineer or something like that. But this industry is here to stay. So don't worry about it. Go flow with the career option that you have taken. There's nothing stopping you from switching it over to environmentally friendly career also. But truthfully speaking, most of the things that we use in our everyday lives come in some or the other form of petroleum industry or byproducts of petroleum industry. So it's not going to be easy to get rid of us, right? So although we will see a very big revolution on AI and IT related spend from the oil and gas industry, carbon capture. So these are new avenues to just grow, right? So start educating yourself in those regards, and I think you will make it, right? So keep up the good spirits and good luck with your exams. Thanks.
Thank you, sir.
Bye.
Thank you, sir. Thank you, sir.
Thank you, sir.
Thank you, sir.